Okay, so in this video I'm going to explain the content of periodic trends. It is chapter 4 in the chemistry unit, and what you have to know by the end of the video or by your exams is the name of the 5 trends, the meaning or what they are, and why they happen in terms of chemical and elements and compounds and structures and bonding and anything that you can be able to prove why the trends happen. So since this content is related to periodicity, which is the name of chapter 3, I decided to just include what periodicity means because a lot of people don't know. So periodicity means the study of trends within the periodic table. And we have to remember that the periodic table was structured in this manner with these elements in this exact order for a reason. And one of these reasons is to help us understand the periodic trends that happen. So we're going to be exploring trends that happen down a group or across a period. And yeah, so the first thing that you must understand is the idea of effective nuclear charge. So the definition of effective nuclear charge is the net positive charge experienced by an electron. So back to chapter 1 and the basics of basics, the red dot in this diagram represents the nucleus of an atom, and it is positively charged, while the black dots represent the electrons of the atom, and they are negatively charged. And since opposite charges attract, these forces actually attract each other. And what you must know for effective nuclear charge is the idea that although there are more electrons within the inner shells of the electron, so for example, carbon has 1 inner shell and magnesium has 2 inner shells, these don't count for effective nuclear charge. Effective nuclear charge is the pull of the outermost electrons, so the electrons that are in the complete outer layer. And you must understand that the electrons in the inner shells will actually provide as a shield and will decrease the attraction between the outer electrons and the inner electrons. So as we can see that carbon has a Z effective or effective nuclear charge of 4 because it has 4 electrons in its outer shell, while magnesium has 2 in its outer shell, and magnesium has 1 extra shell. So determining the effective nuclear charge, this is entirely based on valence electrons, and valence electrons is the name given to the outermost electrons, or the electrons in the outer shell, as I explained previously. And these are just some general ideas to keep in mind when determining the effective nuclear charge. So full shells, the ones that I explained that magnesium has 2 while carbon only has 1, have 8 electrons. Noble gases, which are the elements to the complete right of the periodic table, have full shells, which means that they have 8 electrons. And we should count the number of valence electrons based on the periodic table. So right here, I have a periodic table. I know that these are the noble gases and they have complete shells. And I start from the left of the periodic table, and I know that this group only has 1 valence electrons, or outermost electrons, and consequently, the effective nuclear charge of 1. Because I know that, for example, helium has a full shell, and then lithium has 1 extra electron that is in the outer shell. Beryllium will have 2, boron will have 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon will fill in another shell or layer, and then sodium will once again have 1 outermost electron. So you can see that the trend counts both groups in the s orbital and the p orbital, and they do not count the d orbital. So when counting number of valence electrons, you go 1, 2, 3, 4, 5, 6, 7 full valence electron with 8. So if I ask you how many valence electrons, or what is the effective nuclear charge of silicon, for example, you can go here, and you know that it is the same as carbon, and it is 1, 2, 3, 4. So silicon has 4 in its outer shell. So when we compare the effectives, we can see that helium will have no outer electrons, or 2 outer electrons, depends, because it doesn't have any inner shells. Chlorine will have 1, 2, 3, 4, 5, 6, 7 because it is almost a noble gas. It'll have 7. And for example, potassium, which is in group 1 right over here, will have only 1 in its outer shell. So it is important to consider that the more electrons there are in the outer shell, the more attracted they are to the nucleus. So the first trend that we must analyze is the atomic radius. So the atomic radius is half the distance between 2 bonded atoms. So these are 2 bonded hydrogen atoms, and it is half the distance between them. This is the atomic radius. So the trends and explanations for atomic radius, they increase down a group. And this happens because, as I explained right here, there are more shells as you go down a group. So helium only has one shell, while chlorine, for example, has 2 inner shells. And then potassium has 1, 2, 3 inner shells. So as you go down a group, the number of shells will increase, and consequently, the atomic radius will also increase. Apart from that, they will decrease across a period. So the reason this happens is because they have more attraction to the nucleus. As we explained here, with the Z effective, it'll increase across a period in the periodic table, and therefore the outer electrons will feel more pull and will be more compact towards the nucleus. So right here in this diagram, we can actually see this trend going on. We can see that as a period begins, it is a higher atomic radius, and then it decreases as you get closer to the end of a period, and then it increases again based on the higher number of shells. So if we consider it in the periodic table, we can see that from lithium to neon, for example, the atomic radius will actually decrease because they have more outer electrons that are more attracted towards the nucleus, so there's a higher Z effective. And down a group, they will actually increase because there are more energy levels or shells. A second trend that we must analyze is the ionic radius, and this is half the distance between 2 bonded ions. Ions, I will explain later, are either positively or negatively charged, and it's the distance between bonded ions. So what are ions? Ions can either be positively charged or negatively charged. Cations, they bond and they will lose an electron, so they are positively charged because they lost one electron. And anions will bond and they will gain an electron because they will steal the electron from the other that it is bonding with. Remember that atoms always want to bond to try to get to noble gas configuration. This is what I have explained right here. So for example, lithium will want to get a positively 1 charge, which means lose 1 electron, so that it can go back and be like helium, which is a noble gas. Oppositely, fluorine will get a negative 1 charge because it will gain 1 electron to become neon. So we can just see that these are the charges that the atoms tend to make, which either makes them a cation or an anion. These ones here will become cations, because they will become positively charged, while these will become anions because they are negatively charged. So what are the trends between the ionic radius? So cations are smaller than their parent ions, and this happens because they will lose 1 shell and become smaller, and anions are larger than their parent ions. They will gain electrons, and these electrons will repel one another. So for example here, if I have lithium, the normal lithium has 1 valence electron in its outer shell. When it loses 1 electron and becomes a cation, it will become like helium, and it will lose a complete outer shell. This will make it decrease in size. Contrastingly, fluorine has 7 electrons in its valence shell, and as it gains 1, the extra electron added will actually repel the others and will make the size of the atom increase. So we can see here that the cations are larger than their parents, and the anions are cations are smaller than their parents, and anions are larger than their parents. And also, although all anions are larger than their parents, when we compare 2 different anions, for example, nitrogen and oxygen in their states, nitrogen will gain 2 electrons while oxygen will gain, nitrogen will gain 3 electrons while oxygen will gain 2. We can see that oxygen is actually a bit smaller than nitrogen because there is more attraction to the nucleus, which goes back to Z effective. So since the electrons in oxygen are more attracted towards the nucleus, the size between the anions of nitrogen and oxygen will be a bit smaller. But the important part is cations are smaller because they lose 1 shell, and anions are larger because they gain electrons, and these electrons repel each other. So ionization energy is the third trend, and this is the energy needed to remove the outermost electron from a gaseous atom. So we can see here that there's an electron right here, and they're trying to remove it. So it's the energy needed to remove an electron. That's really important because electron affinity will be the opposite. So the chemical equation will be, you have a neutral atom, and then you will have a positive, and you're removing the electron to make it not neutral. So you're adding one electron to a stable molecule, and it must be a gaseous molecule. That's extremely important. So something to keep in mind, atoms want noble gas stability, as what we said. So we must keep in mind this table here for what charges they tend to make. And they want to get there the fastest way possible. So for example, fluorine won't want to lose 7 electrons in order to get to helium configuration. It just wants to gain 1 electron to get to neon because it's easier. So what are the trends for ionization energy? It'll increase across a period. So why does this happen? Ionization energy is the energy to remove 1 electron. So across a period, you can see that lithium, for example, wants to lose that electron because it wants to go to helium notation. So does beryllium. It wants to lose 2 electrons to go to noble gas. However, fluorine will hate to lose an electron because it is so close to getting to neon. And neon, most of all, will hate to lose an electron because it will lose its stability. So as you can see, as you go across the period, your ionization energy will increase because it will require more effort to remove the electrons because they are already so close to noble gas notation. Apart from that, as you go across a period, the atoms are smaller and the electrons are more attracted towards the nucleus. So the larger attraction will require more force to break. So more energy will be required. And as you go down a group, it actually decreases because there is less attraction to the nucleus. So because of more shells added as you go down the group, there's less attraction between the outermost electrons and the nucleus, and that decreases ionization energy. So it requires less strength for you to remove 1 electron. So there are 2 exceptions that is important to mention in this trend, and you must be able to explain. The first of them is between group 2 and group 13. So you can see those are right here and right here. So it's especially between beryllium and boron. And why this trend happens is because, as we can see here, boron has 1 electron in its 2p orbital, and beryllium has a stable 2s orbital. So group 2 is actually more stable than group 13 because it has a full orbital. So this electron is actually very easily removed so that it gains stability. And that's why, although the ionization energy increases across a group, boron is actually less than beryllium. And the second exception is between group 15 and group 16. And this is because of Hund's rule. Hund's rule states that you have to give 1 electron up and then 1 electron and to all of them and then 1 electron down. And in group 15, which is nitrogen and oxygen, you can see that they have 1, 2, 3 electrons for nitrogen in orbital 2p, and then oxygen actually has 1 extra electron in 2p. And what this ends up happening is that there's a repulsion between the 2 electrons that are in the same box, which causes a repulsion. So it's easy to remove this electron because this is a semi-stable orbital.